So welcome everyone to the ATMCS series of online talks given by early career researchers. So the first speaker today is Marek Filakovský, and the title of his talk is Embeddings and Tverberg-Type Problems, New Algorithms and Undecidability Results.
Okay, can I start now?
Yes.
Okay, hi everyone. So today I'm going to be talking about two results. One regarding the r-Tverberg problem. This is joined with Lukas Vokrinek from Brno. And the other about the classical embeddings problem, joined with Wagner and Stephan Zhechev from IST Austria, where I'm also based in at the moment. So I'm going to shortly introduce these two problems, talk about some kind of history about these problems, and then about the new results and algorithms which we achieved. And I guess that's going to be it. So let's jump straight into it. So the embedding problem. So the problem is as follows. If we are given a finite k-dimensional simplicial complex, we ask, is this simplicial complex embeddable in RT? Okay, just immediately from the get-go, you can imagine kind of three types of embeddings of simplicial complexes, right? So this is the linear type. So we just place the vertices in the space and then, everything then is prescribed by default. Or we can talk about the piecewise linear. So in short, you are able to subdivide the complex as many times as you want, and then ask if this is now linearly embeddable. And finally, you can just go for a geometric realization of your simplicial complex and then ask for a continuous map, which doesn't have self-intersections. That would be the topological embedding. So we're going to be talking about the PL embedding, but actually this will cover the topological embedding as well. I'm not going to go into details on that, but just a side note to this. So we can formalize it and have, okay, this is a problem with two parameters. One is the dimension of the complex, and the other is the dimension of the space which we are going to be embedding to. And the output is just a yes or no if the map is there, if there is an embedding, right? We don't actually output the embedding itself. Sometimes we are able to, but that's not the setting we are talking about. So the new result, well, it actually was published this year, so I guess I can change the number here to 2020. So it's saying that the embedding problem is actually algorithmically undecidable in this range of dimensions. So there's some threshold for the D, we get the greater or equal than 8, and the D has to be less than roughly 1/2 of K. Okay, and we're gonna then talk about details of this. Now regarding the r-Tverberg, which is not as maybe obvious or easy to understand, it's kind of more general version of this embedding problem. So we are once again asking for a map, the PL map from our simplicial complex to the Euclidean space. But now I want the map not to have r-tuple intersection points and between pairwise disjoint faces. Okay, so the difference is, of course, like the embedding is roughly when I ask for two tuple intersection points, but there is also this pairwise disjointness, which makes it slightly different. The difference is not something I'm going to be talking much about, but you just imagine, this is just an embedding for higher, like more faces intersecting at the same time. Just for example, so say r is equal to 3, so I don't want the triple intersection points, and let's say I have k is equal to 1, so this is a graph, it's another graph, there are two cases, and d is equal to 1, so I want to map this to a line, and I ask if there is an r-Tverberg map. So considering the first one, surprisingly, there is one. Just imagine then the line is placed like going like here. So if I project alongside this edge, this will actually, I mean, there will be triple intersection, but not between pairwise disjoint faces. So this will actually work. And you can check for yourself that the other one is impossible in this setting. Just like that these conditions like the pairwise disjointness actually play a role. Now, if I were to subdivide this face many more times, this would probably cause some issues. But that's just for the like visual, what you can imagine. So now the problem has basically three parameters, r, k, and d. So r is the how many intersections I'm allowing, k is the dimension of the complex, d is the dimension of the ambient space, and once again we're asking for a map. Now our result, joined with Lukas, is that the r-Tverberg problem is polynomial-time decidable in the following range of dimensions. So I'm saying that d has to be greater or equal to So r plus 1 over r times k, roughly. Now, if you're going to plug your r equals to 2 here, you're going to have like 3 divided by 2, so 1.5 times k. It's the same bound as we had before, but just the opposite side, right? And that's no coincidence, and we were going to talk about it a bit more. So let's go into the details about these two problems. So the embedding problem. So first I'm going to just talk about what the status quo of the problem was before us, before we stepped into it. So this is the table for the first couple of dimensions and dimensions d and the dimensions of the simplicial complex k. So it looks like this. So the first, let's talk about the beginning. That's 1 and 2 and 2 to the 2.
Marek, excuse
Yes?
me. So we just have one question. Are we
Yes.
only considering 0?
Yes, 0 what?
So let's see. That's
Okay.
that's where it stops.
We might need Shmuel to say a little bit more in the chat window, and then we can.
Okay, I'm good.
Interrupt again.
Can you?
Yeah.
Yeah. Okay. So maybe. Okay. Can I go on or?
Okay. Yeah. Go for it. Sorry.
Okay. So the nice example of the embedding problem. Just reminder, we're back at the embedding problem. So the graph planarity, right? So we have a one-dimensional simplicial complex, and we ask if it's embeddable in R2. And this is actually decidable in linear time. So we have, so this is linear, this is the sigma L, this is the legend. And actually this can be extended to two-dimensional to two-dimensional. This will also turn out to be linear time. Then just by dimension counting, you can just observe.
So Marek, I'm sorry again. So it's only PL embedding.
Yes.
Okay. Thank you.
Yeah, sure. So if D is greater than 2k, we are always able to PL embed. And if k is greater than d, actually, so I'm mapping something, say, 10-dimensional to something 2-dimensional, you can probably imagine this will create some self-intersection. So this is like this always, this green part, and never the gray part. And the other results are, so by Dumesme, Riek, Zhechev, and Tanzer, if d is equal to 3, so we're here, and k is 2 or 3, so this problem is NP hard, but however, by Matuszek, Zhechev, Tanzer, and Wagner, this is also decidable. So it's kind of surprising result there. And then we have a result about undecidability, which is this red part. Red because it's bad, I guess. So this is undecidable problem for d greater than 5, and k is d, and k is d plus 1. This is based on the sphere recognition problem. And the rest here is NP hard. Now, what I haven't mentioned is this blue P thing, right? This P, which means it's polynomial time, and this is this 1.5 range dimension, actually. And because I'm going to be talking about it more in the r-Tverberg problem, let's just jump into it, what happens here. So this is the so-called metastable range of dimensions. So let's just step back and say, okay, I have an embedding. So given an embedding like that, let's say it's a, let's say I pass to the topological situation and take just the geometric realization.
Well,
It works for
Marek,
PL as well. Yes?
Excuse me again. So we have another question. So I don't understand R tuple intersections. Two simplices intersect in either 0, 1, or infinitely many points, no?
Let's just, no. Yeah, they can intersect infinitely many points, but the point is if only 2 of them intersect, then this is an intersection of the 2, right? I'm not counting it infinitely many times there.
Okay. Yes, perfect.
Fine.
Thank you.
No problem. So, so I can define this map. So I can take a product of the simplicial complex with itself and delete the diagonal, and then I can define the map f hat as follows. Now it goes to a sphere of dimension 1 less. This is a continuous map, by the way, yeah? And the group Z2 acts by flipping the coordinates here. So we have x and y coordinates, it flips them. This is a free action, and acts antipodally on the sphere as well by antipodal action. So every time we have an embedding, I will have a map like that. But what the main result in this area is the Hefflicker-Weber theorem. So when I'm in the so-called metastable range of dimensions, when d is precisely greater than this 1.5 times k, roughly, when I have a map like that, when I have this equivariant map, there is an embedding. Okay. So kind of we turn the question about the existence of embedding to existence of some kind of equivariant map. And by result of Chadek, and Vokrinek, so they studied precisely the set of homotopy classes of equivariant maps with free group actions. And what they had was they had an algorithm which under some dimensional conditions, which are going to be satisfied in the metastable range actually, would tell you whether the set is non-empty. So it will tell you if a map like f hat exists, to boil it down. And because the algorithm is polynomial time, I would be able to answer the embedding problem in polynomial time. So this is the conclusion, and that just explained the last part. This is the p part in the table, and the table, by the way, goes like this to infinity. Like you will have these two undecidability at the bottom and p hardness in the middle, and the polynomiality here. So what is new? Where does our result with Uli and Stephan fit in? Is the following. So the embedding problem is undecidable, kind of below the range, and now it looks like this. So the new undecidability I painted a bit different colored. So what happens? We have some unresolved cases where we only know NP hardness in low dimensions. And then every 2 steps, there will be this tiny gap, which we don't actually like here, because otherwise we would have like a nice dichotomy between like solvability and unsolvability. But yeah, we're working on, this is a work in progress, right? So, but otherwise it's undecidable. And I'm going to just very briefly go into how we do this undecidability and how it comes about, okay?
And the red-orange means the same, the red U means the same thing as the orange U, except the orange U is the new part that you've added.
Yeah, the orange U is new part, the red part was before. Just check. This was before,
right.
And this is new.
Very
okay?
nice.
When we formulate the result like it's undecidable for everything, but actually this is covered. This was known already. We can use our result to show the undecidability here, but it's kind of pointless anyway. So let's go into it. So the undecidability comes from Hilbert's 10th problem. So we're giving so the problem is roughly like that. You're giving a set of Diophantine equations. So you have, it's like polynomials so in multiple variables. You have integer coefficients, you have a system, so you have multiple equations, right? And then you ask for an integer solution. I mean, I don't know if the system has an integer solution. I just typed it out to LaTeX. You can check it out. I guess it doesn't. But anyways, so do you have a generic algorithm which would solve any system like that is the question. And this is an undecidable problem, quite famously by Matiasevich in 1970s and building on the work with other people. So what we actually use is a reformulation. So Chadek, Kachal, Vokrinek, Matuszek, and I guess Wagner was there as well. So what they did was they will, given a system like this and picking some m, let's say m is even, so they redescribe the system as a question whether we can figure out a continuous map which would make a diagram like this commute, which is quite fascinating. So now commute up to homotopy, right? So you have some wedges of spheres and maps between them. This is f and g. So they all describe the system, any system. And then if there is a solution to this problem, so if there is a map, continuous map like this, which would make it all commute up to homotopy, then actually the system would have a solution. So this is nice equivalent formulation. Actually, if m is odd, you just change it a tiny bit, but you can do the same trick again. So you can also redescribe it as a system like this, if you so desire. So we're gonna only be talking about the first case. So let's say, okay, m is even. So just how do we do the embedding problem undecidable? So we start with a formulation like this, problem like this, and say, okay, finding this map, this dotted arrow, it's actually equivalent to taking a mapping cylinder, the double mapping cylinder of f and g. So it's like roughly I'm gluing every information in this part together, creating this bigger space. And I'm asking, is there a way I can kind of collapse the entire space onto this SM part, onto this part? This will be equivalent. Okay, so that's one way. The next trick is actually interesting. So if we add this disjoint sphere, SL, L is just some other, let's say, higher dimension. Now, the original problem is now equivalent to saying, okay, can I map my let's say these pens, this double cylinder joined with this external sphere to a bigger space. There's a sphere of dimension going to be 2m plus l plus 1, such that this red part and this blue part are going to be linked. So they're going to be kind of like orthogonally complement to each other in a way, right? And the only problem there is if I take this as my simplicial complex and just ask for an embedding to this higher dimensional space, you will always be able to do it. But the problem is the red part and the blue part have to be in this nice position such that they are linked the right way. So the final ingredient of our construction, yes?
The diagram looks very much like cobotism and surgery. Is any relationship to what you're doing in that?
I mean, it's a homotopy theory. So no, it actually isn't. So the double mapping cylinder is just taking mapping cylinder of F and mapping cylinder of G and gluing them on their bases. It's very
oh,
easy.
okay.
Yeah, so that's, I mean, it's a nice picture.
Okay.
Courtesy of Stephan, I must point that out. Okay, anyway, so finally I'm adding this gluing part, this which we call like a scaffold, which makes sure that no matter how I embed this, the M and L sphere are going to be linked the right way. So this is how we define the simplicial complex. Just so whenever I have now the embedding of the simplicial complex with this sphere of dimension 2m plus L plus 1, but you can say this is just omit a point and this is the R to the 2m plus L plus 1. So this will be the same as finding a solution to a system of Diophantine equations, which is undecidable. So this is all undecidable. Okay, so this is the conclusion. So let's just very briefly go through the r-Tverberg. So how is the story going out there? So, okay, we all know how it works for r equal to roughly now, but let's say r is a bit more. So the diagram looks kind of like this. So there's this tiny, so okay, the green part is the same. You just dimension count how much can it self-intersect r times with each other, and you will have this bound, which is r over r minus 1 times k. So this is the always bound. Then there's the never bound. Now, the problem is the pairwise disjointness makes it slightly different, but seems nobody in the community actually cares to know precisely these bounds. So you can I guess, work it out yourself if you want. But I guess it's like 1 over r times k there. If I were to be strict and not have the pairwise disjointness, but just normal, then it would be equal to k. And then I have this r plus 1 over r times k, and we already saw it. This is the metastable range. And our result with Lukas is precisely, okay, the r-Tverberg problem is going to be polynomial time between these two lines, between like roughly r plus 1 over r times k and r over r minus 1 times k. So just to inform you what we actually do in our results, it's a bit different, okay? We again talk about equivariant, some homotopy classes of equivariant maps. We do a bit more of like model categories and a bit more knowledge is required. But let's just say if you're given finite simplicial complexes and you describe an action of a finite group on it, then we have an algorithm which would compute the set of equivariant homotopy classes of maps between x to y, from x to y, under some so-called stability condition, right? So the dimension of fixed points of x has to be less than twice the connectivity of fixed points of y, okay? So the difference between what we had previously, what was used for the r equals 2 case is actually the action of the g can be whatever, whereas previously, the result by Zhechev and Vokrinek, where they did the polynomiality for the embedding problem, they had to do the freeness, right? The action there had to be free. And actually, this is no easy generalization how we achieve this. Okay, just like what we actually did was something about diagrams of simplicial sets, and we got the group action as a kind of corollary of what we did, but that's not important. So how it works in the metastable range is how we use the theorem actually. So if we're giving this r-Tverberg map, we can always define this map f hat as kind of previously in a kind of similar way. I can take an r-tuple intersection point, r-tuple intersection of the simplicial complex with itself, r-tuple product, I should say, sorry. And then I delete the diagonal, so any sort of intersection. So the space looks like that. These are r-tuples of simplices of k, such that they are pairwise disjoint. And there's an action of my symmetry group on this. It's actually free on the first part, but it's not free on the sphere. And this is where we need to use our theorem and can't use just the Zhechev-Vokrinek result. And okay, metastable range would be useless if I couldn't kind of reverse the arrow. Whenever I have r-Tverberg map, I have the f hat, but we need the opposite. And this is courtesy of Isaac Mabilla and Wagner from 2016, where they established the generalization of Heffley-Weber in this context. So actually, in this metastable range, the r-Tverberg problem is equivalent to determining if this map exists. Okay, if this f hat exists, then I actually have an r-Tverberg map, similar to what we had in the embedding. So can we decide about the set is non-empty? And we've already seen that this is what our algorithm does. We just need to check that the fixed point sets are the right dimension and connectivity. So it's positive. And yeah, that's all. This solves this kind of answers how we did that without actually describing it. So that's all. I included a couple of references. My work joint with Lukas is sadly not yet published, but you can look at how they did the polynomiality previously in the embedding problem, and I guess this will give you some insight. So it should be published. I mean, definitely it will appear on arXiv soonish, so that's your chance to take a look at it. Okay, thank you.
Okay, thank you. So maybe before we go to questions, I would ask you to unmute yourselves and clap for Marek's talk. And now you can remain unmuted and ask questions.
I had a question, Marek. So is it correct to say that in the first problem, a lot more is known than in the second problem in terms of which cases are polynomial or NP hard or undecidable,
yes.
etc.?
Yes. I think that's a fair assessment.
So there's in the second problem, there's no regions that are known to be undecidable yet, or I guess the very bottom region was.
Well, that was just impossible, right? That's not undecidable, it's just impossible, right? You can't do it.
I see. So
it's decidable quite easily.
No.
It's yeah. I guess I should have pointed at some like bright color. Anyway, yeah. Well, that's something I'm working on, right? At the moment, I would like to see how it works for the r-Tverberg problem there. I hope it will be similar, but who knows?
Very cool. Thanks.
More questions. So I said you can unmute yourself, or you can also just type in your questions into the chat window. Okay, so
can I ask a question? I was just wondering, is there anything easy that you can say about the motivation for considering this r-Tverberg problem rather than just when r is 2?
Well, motivation, like, so there are number, so in computational topology, in like the combinatorics, the Tverberg and Tverberg-type problems about these multiple intersections are actually studied a bit more. Okay, the context can be a bit different, but there is some research in that. For us, the joint work with Lukas wasn't really aimed at solving the problem per se. It was just like a lucky side result initially. So yeah, so I would be saying there is a motivation in like in combinatorics, but it's just not the angle I like arrived there. So I don't know. That's something I'm looking at as we speak. Not literally. Yeah.
Okay, thank you.
more questions.
Hi, Marek. I was wondering if you could give a quick intuition why the problem of solving the differential equation is the same as solving this homotopy commute diagram, kind of.
Oh, okay. So I actually would. So in the references, I added the paper. I'm just gonna quickly. This will be chilled there. So I'm just to say the extent of this is the first one, right? You can read it there, and it's really nice. So, but what you can do is you can first basically add new variables. So whenever you have the system of Diophantine equations, you can always reduce the system to a system at which you have more variables, but it's quadratic. And then you can actually force it to be of like a very specific form, right? And then the trick is in, so the number of equations is actually described by, if you have this wedge sum, so this is just one of those wedges. So just one equation is described by one of these wedges, and then you use some information about Whitehead products and homotopy groups of spheres. So if you looked at there was some kind of notion, I don't know, can I go so far behind? Okay, yeah, you see for these m greater than 2 and odd, the reason why you need to have a wedge sum of two spheres and not just the single one is here is there's something about the homotopy group of this sphere, and which is different when m is odd and m is even. So there's something generated by these Whitehead products and generate some kind of subgroup, and this is an infinite order here. But then if I were to go odd, it wouldn't be of infinite order here, so it would be actually solvable. But if you take a wedge sum, then it has something which is an infinite order. It's a nice game there. And it's not hard to read, actually. It was nicely written. So yeah,
Okay.
That's the insight.
Wonderful. Okay, thanks.
Okay, I think we have time for one more question, if there are questions left. Okay, so if there are no questions, then Marek, thank you again.
It's been a pleasure.